Now that we've seen the definition of the Laplace transform, let's do a couple more examples to try and understand what various Laplace transforms look like and what kind of things we expect to see when we look at Laplace transforms for signals that we care about and systems that we care about. So the learning objectives for this little section are going to be to use the definition to compute Laplace transforms and to be able to identify the region of convergence. Now remember, in order to really properly define a Laplace transform, as I said before, you need to be able to identify both the formula for the transform and the region of convergence for the transform. So let's look at our example from before. We looked at a decaying exponential, e to the minus 2t u of t, but we can generalize this to sort of any scalar a. So if we look at signal h of t is equal to e to the minus at u of t, we can do the same trick we did before. We plug it into the definition of the Laplace transform. This u of t is going to make this integral go from 0 to infinity. And then we gather these two exponents over here, and so we get e to the minus s plus a t dt. And here, in order for this thing to converge, we need the real part of s to be greater than minus a. So here they actually have a pole at minus a because we're going to get this transform s 1 over s plus a. So here we have this pole here at minus a. So this is the general formula for a decaying exponential. We get a single pole at the exponent of the exponential. So what about the unit step function? So the unit step function is another simple function. And remember, this system is the system corresponding to the impulse response u of t is an integrator. This is an unstable system, as we saw before. But we can simply plug it into the formula again, and we're going to see that again this u of t is going to make the u of t makes it start from 0 to infinity, and we get e to the minus st dt. The integral of that is just 1 over s. But now we need the real part of s to be greater than 0, and you can sort of see this as an example when a is equal to 0 in the previous example, but kind of helps to do it on its own just to sort of plug in the integral and see how it works. So here, the region of convergence is just going to be the right half plane in this marked in yellow here. Okay, what about anti-causal systems? So we can take this kind of weird looking system, minus e to the minus at u of minus t, right? Again, we can just plug it into the formula. Now this u of minus t is going to make the integral actually go from minus infinity to 0, because u of minus t, remember, looks like this. So this u of minus t is going to go from minus infinity to 0. So this is u of minus t. And we have minus e to the minus s plus at dt. And so now, since we're integrating from minus infinity to infinity, we actually need this thing, this s plus a has to be less than 0, which is to say that the real part of s has to be less than minus a, right? So this is again a pole at minus a. Here's minus a, but the ROC is going to go actually the other direction. It's going to go from minus infinity to minus a. So if you notice, we're getting the same formula here. So this is as we did before, but the region of convergence is different. So this is actually an interesting property of Laplace transforms that we need to understand a little bit better. So we have two signals which have the same transform. That is, they have the same formula for the transform, but they have different regions of convergence. So that's why I make and emphasizing yet again the fact that to define a Laplace transform properly, you need to define not just the formula, but you also have to define the ROC. So again, we have these s-planes which are going from, so for e to the minus at u of t, we get this region of convergence that goes to the right of minus a, and for minus e to the minus at u of minus t, we get the region of convergence going the opposite direction. So it helps actually to kind of take a look at what these two signals look like. Always draw a picture, right? So e to the minus at u of t kind of looks like this. But what about e to the minus at minus e to the minus at u of minus t? Well, let's look at t equals 0. At t equals 0, this is minus 1. And then and it's 0, it's going to be 0 for positive t. But e to the minus at for negative t is blowing up, so it's blowing off exponentially this way. So this signal here we can see is kind of blowing off as it goes to minus infinity, and therefore the region of convergence only makes sense if we make sure that s is sufficiently negative, and that's why we get this region of convergence that's going to the left here. Let's do one more example. So let's look at a cosine. So like h of t is cosine omega t u of t. So remember, the first thing you see when you see a cosine is maybe think about Eulerizing it. So let's Eulerize it. We Eulerize it into a sum of two complex exponentials, and then we take the Laplace transform of this. So we plug in this whole signal into the definition of the Laplace transform. Then we have our e to the minus st dt here. And then we can split it up into two integrals. We integrate this term and integrate this term. So we get something like this and something like this. And then again, doing our, using integrating exponential functions. Remember, the u of t is making these limits go to 0. Then we have a half s minus j omega plus a half s plus j omega when we do these integrals. And then if we cross multiply and put these two together, we get a final formula which is s over s squared plus omega squared. So there's a degree 2 polynomial. So this is degree 2. And it has 2 roots. So therefore there are going to be 2 poles in this transform. So let's take a picture of what does the s-plane look like for this particular Laplace. So here we have it. We have poles at s equals plus minus j omega. We have this particular transform pair. Cosine omega t u of t goes to s over s squared plus omega squared. As a little bit of exercise, try and do this for sine of omega t, and you'll get a very similar looking formula. But what we can see here is here are poles at plus minus omega, and then there's a 0 at s equals 0. So this is a 0, and this is how we draw what we call the pole 0 diagram. This is a pole 0 diagram. We put zeros where the numerator is a 0, we put a little circle, and then we put an x where the poles are, and the poles here are at plus minus j omega. So, of course, the best way to kind of get some intuition about doing Laplace transforms is to derive a couple of Laplace transforms on your own. So in addition to doing this sine of omega t, you can do the same Eulerization trick as we did before. Try these other ones. So here's one involving 2 exponentials. And here's one which is a little bit more complicated that involves a decaying exponential times a cosine, and so for that you'll have to do again some Eulerization. And it's a little bit more messy algebraically, but the point is to kind of derive these once, and then there is a transform table that you can use to simply look up the transforms that you need when you need to do a Laplace transform. And the point we want to get to is less about manually computing Laplace transforms and more about analyzing and understanding what is the Laplace transform telling us about a signal or about a system. And so to get that, we have to still build up a few tools and build up some intuition. And once we're there, then we can start understanding better what's going on when we try to, for example, design systems to accomplish a certain task. What is that going to look like in terms of the pole 0 diagram, and what is that going to look like in terms of the actual system impulse response that we are going to get in order to implement that functionality.